All right, y'all. Unit 1, Day 5, Continuity, Take 13. Today we're going to be talking about continuity, a topic that you already know a lot about from pre-calculus. We're going to take your pre-calculus knowledge and we're going to take it up to a calculus level and be able to apply a limit-based definition of continuity. It's a three-part definition, and we're going to look at applying it graphically and analytically to determine if a function is continuous at a point. Start with some continuity 101 review. A function is continuous if it has no abrupt changes in values. That means it has no breaks, no holes, and no vertical asymptotes. So if you look at this first example here, we're discontinuous at x equals c, because if I look at what happens at c, we're not even defined at c. So I'm just going to call that because f of c is undefined. Got to be defined to be continuous. If we look at number two, discontinuous at c, because if I look at x equals c, we have a jump discontinuity from that the black filled in circle to the open one below it. We would call this a jump discontinuity. And in part C, we are looking at a vertical asymptote, discontinuous at c because we have a vertical asymptote. We have limits that go to infinity. And finally, what we would call C, it's kind of like a jump. You could call it a jump, or we could just call this a point discontinuity. So those funky ones where it's just undefined at one point, discontinuity. You get the picture. The rule of thumb here is that if you are drawing the function and you have to pick up your pencil, you just found a discontinuity. You found a place where your function is not continuous. So that's like Algebra 2 pre-cal level. Here's how we're going to define continuity in calculus. It is a three-part definition. I put this in like size 20 font. Because obviously it's really important, and you're going to be talking about continuity a lot. When we go on to prove a lot of the core theorems of calculus, they only apply if your function is continuous. They only apply if your function is smooth and you don't have to pick up your pencil while drawing it. Those three steps. Number one, you have to show that f is defined at the point C that you are trying to prove continuity at. You have to show that the function is defined at that point. Number two, you have to show that the limit exists as x approaches that value c. And number three, you have to show that those two things are the same. So you can sort of use the filled in hole to imagine this analogy. We have to show that the limit exists. So we have to show that the limit from the left and the right are the same, and we have to show that we're defined at exactly that point. The limit exists and we're defined. If we can show both of those things, we've shown continuity. So we'll do a couple examples here. If I have this graph here and I was asked, is f of x continuous at x equals -8, right? This is more than pre-cal. Pre-cal, you would see that and you'd say, oh, point discontinuity? No. What I'm looking for here is proof, and here's how I would prove this. I would look back at my three steps, or I'd have them memorized at this point, and I would say, okay, first thing, what is f of -8? I don't have to write a lot of words, but I just need to write out what these things are. I don't need to talk about how I know this. I see f of -8. Well, we've got that dot there, and that dot has a y coordinate of 4. So I know that f of -8 is 4. Number two, I'm going to say that the limit as x approaches -8 from the left of f of x. Okay, let's look at that. From the left, that's -5. The limit as x approaches -8 from the right is also -5. Therefore, the limit as x approaches 8 of f of x is also -5. So it passes step 1. F of c is defined. It's f of -8 is 4. It passes step 2, the limit exists. However, it fails step 3. And the way I would prove that it fails step 3 is I would say f of -8 does not equal the limit as x approaches -8 of f of x. Therefore, three little dots, therefore not, let me be super professional here. F of x is not continuous at x equals -8. So we're taking what seems like a pretty intuitive definition. Oh yeah, can't pick up your pencil. No breaks, no jumps, no holes. And we're making it super, super, super formal. You show what the function is defined as at that point. You show what the limit is. And if they're the same, you can say they're continuous. So really quickly here, an example of what that would look like when two functions are continuous. Let's look at what's happening as x approaches -6. Is f of x continuous at x equals -6? One, I would say f of -6 equals, it's the bottom of this right here. That looks like -7. I'm going to show you a technique. I showed you like fully formally in that last one. Here's something that would also be totally kosher on that exam. We could say the limit as x approaches -6 of f of x equals the limit as x approaches, from the left equals the limit as x approaches -6 from the right of f of x equals -7. Therefore, limit as x approaches -6 of f of x equals -7. And finally, step 3, proving continuity. F of -6 equals the limit as x approaches -6 of f of x, which equals -7. Therefore, f of x is continuous at x equals -6. So that would be, I've seen a lot of work come in from the quizzes that's really good, and it's like a paragraph long explanation of how these limits work. But the more and more you can transition to just writing mathematical statements, you never want to be talking in the AP exam about, I moved my finger on the line and I saw that we were getting closer and closer to this many values. Not because that's wrong, but because the more words you say, the more likely they are to find a word they don't like and to take off a point there. So you want to stick to just the bare basic facts that are necessary. In this case, those bare basic facts were f of -6 is -7. The limit as x approaches -6 of f of x is -7. Those two things are the same, therefore continuous. And I said that by literally like the only real words I wrote on that paper were is continuous. Everything else was a symbol. Analytically, similar idea. If we had to show whether or not g of x is continuous at x equals pi, I'm going to keep throwing these in here just to get you in the mindset of like, yeah, you should expect to have to look up the unit circle occasionally. So I'll draw a circle here and we'll come back to it when we need that unit circle. All right, is it continuous at x equals pi? So the first thing I want to know is, what is g of pi? This has my or equals sign, so g of pi is e to the pi times the tangent of 3/4 pi. Okay, well, 0, pi over 4, pi over 2, 3 pi over 4. In this case, it's not actually necessary that I remember that these two coordinates here are cosine -√2/2 and sine of √2/2. As long as I remember that they're the same and that tangent is sine over cosine, I know that this is -1. So this is e to the x times -1. Don't freak out about that yet. You'll just get better at it throughout the year. But using the unit circle there, that's -e to the x. So we have part 1. Let's look at the limit as x approaches pi from the left of g of x. So if we look from the left, we're looking at this less than sign here. We're looking at this less than sign, so we're going to plug in, this is going to be e to the pi times the cosine of pi. Now I'm going to throw this one to you, right? Think about your unit circle. Take a second. What's the cosine of pi? Cosine of pi is in fact -1. So we're going to have e to the pi times -1 equals negative e to the pi. Oh, that reminds me there. Hold on. I never plugged in for this x exponent here. So if I go back to this last one, I can't leave that x. I got to plug in for these exponents too. This is going to be e to the pi and negative e to the pi. You have to plug in everywhere there's an x. So far we're good. F of x equals the limit from the left. Let's see what's happening with the limit from the right. Limit as x approaches pi from the right of g of x equals, so now we're back to we're using our other function. We already plugged in pi. We kind of already know exactly what this is. If we are approaching from the right, we would have e to the pi times the tangent of 3/4 pi. We already know that this is negative e to the pi. So what I would say here is that g of x is continuous because, is continuous at pi because the limit as x approaches pi of g of x equals g of pi. If you can show that those two things are the same, you've proven continuity and you're good to go. One more, it's like I'm writing slightly less and less each time. You want to err on the side of writing more. As we get closer to the AP exam, we'll talk about what counts and what doesn't. In this case, you've shown you know the left and right hand limits. It's okay to say here just what the limit is. That's plenty for that one. One last one here. Just what another type of problem that you could have here is finding missing values based on continuity. So let's say we had f of x is a piecewise function less than when x is less than 4, where ax equals 5. When x is greater than 4, it's x squared minus x. For what value of a is that function continuous at 4? So same thing. I see that word continuity, and the first thing I say is, okay, what is f of 4? F of 4 equals or equal to here. So we're going to have, this is x squared minus x, 4 squared minus 4. 16 minus 4, this is going to be 12. And in order for this to be continuous, this has to be equal to the limit as x approaches 4 from the left of f of x, right? Because that's the one that's going to get us to use this other function. That's equal to a to the x plus 5. And so if this is a continuous function, I need the limit from the left to be equal to what the function is defined as. Those at a minimum need to be equal to each other. So 12 equals, and I said oops because I started to write this a, and then I'm like, oh, okay, I forgot to plug in that 4. So this is going to be 4x plus 5. 12 equals a times, oh, not 4x. A is what we're trying to find. A times 4. Plus 5 is a times 4 plus 5. 7 equals 4a. A equals 4 divided by 7. So that's how you could solve for a missing value. If you know that a function is continuous, you can kind of infer what that applies about the function. Let's look at 2 real AP questions to close us out. Let f be the function defined above. For what value of k is f continuous at x equals 2? I'll pause the video here, take 2 minutes to try and solve this problem. That's about how long you'd have on an AP exam, and come back. Okay, so for what value of k is f continuous at x equals 2? Well, when x is 2, we're at k, and so we need the limit as x approaches 2 to be the same thing. And so the above function says as long as x is not 2, we're following the above function. So what we actually just need to find is what is, and again, this is multiple choice, how much work you do here is really up to you on the actual AP exam. So we'd have the limit as x approaches 2 of this top part, 2x plus 1 times x minus 2 over x minus 2. If you try direct substitution, you get a division by 0. You get 0 over 0. This is already factored for us, though. We can cancel this. So the limit as x approaches 2 is 2 times 2 plus 1, that limit is 5. And so if the limit as x approaches 2 is 5, and at x equals 2, f of x is k has to be 5. What you can imagine is it's like the rest of the function is the line 2x plus 1, and there's a hole at 2. There's an open hole at 2, and you need to fill it in with 5 to make this function continuous. 5 is the only number that would make it continuous. Otherwise, if k was up here or down there, we'd have a point discontinuity. All right, last one for today, from 1985, a good year. For which of the following values of following values of x is f not continuous? Take a couple minutes here. Where would this function be not continuous? And come back. Okay, again, this would be multiple choice. If I was just doing this, I would mostly just kind of look at this in my head and think about the following. What is the limit from the left and what is the limit from the right at each of the places where this function joins together different parts? So let's think about it 0. The left-hand limit, we're using sine of x and sine of 0. Super quick unit circle. Sine of 0 is right here. Sine is up and down, so sine of 0 is 0. The right-hand limit, we're now on x squared. 0 squared is 0. Okay, so 0 is good because the left-hand limit equals the right-hand limit. Let's keep going. At 1, we already know the left-hand limit is 0. We kind of already know that from this. Now, when we approach 1 from the right, we're on 2 minus x. We are on 2 minus, oh, no, that's not right. At 1, we are plugging into x squared. We have a left-hand limit of 1. That comes from 1 squared with x squared. As we approach 1 from the right, we're on 2 minus x. 2 minus 1 is also 1. Now we go on to what's happening at 2. At 2, from the left, we're on 2 minus x. 2 minus 2 is 0. From the right, we are on x minus 3. 2 minus 3 is negative 1. And so the answer to this question would be only at 2 are we discontinuous. Because if I look at all the other breaking points, the limits from the left and the right are the same.